Hello, good morning. So today, continuing in our unit of learning the language of math, last time we looked at the order of operations with what are called the integers and real numbers. And to give you some context for that, let's kind of recall, from last time. So what did we look at? We looked at the order of operations. We said first order of business is parentheses, or what we call grouped expressions, because we saw that there's sometimes that you have brackets and it doesn't mean that that comes first, because brackets sometimes mean multiply, right? So context is important as always. 2 was exponents, something like 2 to the third power. That's superscript, which means repeated multiplication. And we had multiply and divide, and then we had add and subtract. And for these, we knew that you have to work left to right because they're of the same tier, they're of the same priority, right? So, but we did this with integers and real numbers. And just so that we're clear, when you hear these words in the future, the integers are the set of numbers that you see on the number line, like -4, -3, -2, -1. They're whole numbers, but it includes, not really to scale there, it includes the negative numbers that are whole. And when we talk about the real numbers, in a brief way, it means it includes all the numbers between those. So we might have 1, 2, 3. We've got -1, but we also have 1.01, 1.99999, etc. So all the decimals that are in between, we include all of those. Okay, and that includes in the negative numbers, right? -1.1, -1.2, -1.21. Infinitely many numbers there are between 0 and 1. So these are the real numbers. We use these, in the real world mostly. Integers are when we're representing things that are kind of more whole or unitary. And today we're going to be looking at fractions. Okay, and fractions are, in a way, a different kind of number, but at the same time they behave the same way as other numbers do with our operations, with our priority list of actions. So first of all, I wanted to give a quick history because I think it's fascinating of where fractions came from. We see the first evidence of this type of thing back in like 1800 BC with the Egyptians. They literally had pictures that symbolized different powers of 10. They still had a base 10 number system, which means basically that 10 is like the most divisible number, and we base our decimal places and our power on tens. And so we see evidence of this back to the 1800 BC, but we see all these different variations and all these actually problems with representing fractions using these partial notations until about the 17th century. And this current notation that we have of, a over b, or, 3 over 4, and we'll talk about what that means. This didn't exist again until around the 17th century, and this actually emanated from Arabic cultures, even though there had been so much other influence from the Indian culture, Babylonians, Chinese, all different sorts of contributions, but this is the notation that stuck because it is clearly the best. And if you go back and look at some of those other images, you'll see why this is the best. It's very clear. So let's talk about what is a fraction. What does it mean, 3 over 4, quickly? And again, some of this might be review. Just take it at the speed that it is for you. So what does it mean to be, 3 over 4? So what does it mean? Well, I like to think of it like this. This tells you the amount that you have, and this bottom number, we call it the type. In mathematics, we call this bottom number the denominator, And so I want you to think like denomination. And when you think denomination, for me, that brings up two things. It brings up a religious belief, and it also brings up the amount of money or the type of money, right? And what denomination? Is that US dollars? Is it in 20s? Is it in 10s? So, and that's kind of the idea I want you to think of the denominator as. It's the denomination. How many 20s do I have? How many 50s do I have? How many hundreds do I have? So in this case, how many fourths do I have? I have 3/4. One way this is typically visualized is slicing up parts of a whole. So if I have a given whole item, again, whatever this might be, fourths suggests that I've cut it up into 4 pieces. So this is where the type comes from. So I'll do that in blue. And then how many I have is 3 of those. So I have 1, 2, 3. So that gives me 3/4. So now you can take this and extend it to any other sort of break. So here's, 1/2. This whole has been sliced up into the type of 2. It's been split in half, and I've only got 1 part. So here's some interesting questions of things to consider. So what does 2/2 look like? Well, I would take my whole, slice it into 2 because that's my type, right? This is how we're slicing up whole things. And how many of those parts do I have? 1, 2. So this is really the same as 1 whole. So what this tells us is that 1 is the same as 2/2. And this is a huge idea, because what this tells us is that any number that I have over the same denomination is equal to 1. And 1's a really nice number, right? You multiply anything by 1, you get back itself, right? You get back the number you multiply by. We call it the unit. It's simple, it's nice. Adding 1 is nice, and multiplying by 1 is nice. So if we see something that has the same number over itself as common factors, we can reduce that to 1. We do it in a particular way, so we got to be careful, but this is a really, really nice feature of fractions. So if I had sliced this up instead into, let's say, 6ths, right? Think about what the type would be here for this particular representation. Well, the type would be, since there's 6 slices out of 6, and how many do I have? I have 6, and you see that this is still equal to the same whole. So this is all equal to 1. So this is, right, whatever you want this, whatever number you see over itself, it's going to be equal to 1. Okay, so this is a very powerful idea. And we use this to do a lot with fractions manipulation. Okay, so what does this mean? Well, we've talked about what it means, what a fraction represents. It represents parts to whole, and we're starting to see some different things that can happen. So when the top number is less than the bottom, we know that we're talking about some number that's less than 1 whole. We can also have it be the case that if I had 5/3, what would this look like? Well, if I am talking about things being sliced into 3 parts, that would look like this. But I have 5 of them, right? So if I go in and shade 1, 2, 3, I still have 2 left. So we must be talking about something bigger than 1. But we're still in the denomination or the type of 3, and I need 1, 2 more of those. And so I see that I've got 5 of these pieces with 1 missing. Another way you could write this is 1 2/3. There are times where this is called a mixed number. There are times where we like looking at mixed numbers, especially when it comes to measurements of medicines or lengths or whatever it is. But a lot of times in math and pure math, we're going to be fine with what we call improper fractions. We will forgive ourselves for the rudeness of improper fractions because they're easy to work with. In order to do operations on fractions, you need them to be in this form. If they're in mixed number form, you need to convert them back. So that's why we typically stay kind of in this arena if you have a fraction that's improper or you have more on the top than the bottom. Okay. So why do we care about fractions? Fractions are huge because they compare quantities. And this is how they were invented. They started off looking at the idea of trading fairly. What item is worth how many items to another, right? So if 3 bags of salt, well, how does that equate to pieces of silver? And then, well, I have really 3.5 bags of salt, so how do I compare these things? And so this idea of comparison is really important. And really, like trade and land and inheritance, this is where a lot of algebra emanated from. But since it worked so well to abstract that idea, this is where all that power of mathematics kind of bled into all the other innovation that we have. It's why you have a phone in your hand or a computer in front of you right now. So, but this is where it got started. So this idea of parts to whole. So with that, they do work like other numbers, but we have to kind of take care to preserve their shape. In a pinch, oftentimes, and we do this all the time, you can move to the decimal equivalent. What does the fraction bar really mean? The fraction bar really means, so if I have A over B, this fraction bar really means division. And we saw this in some of our order of operations problems. So in a pinch, we could say, 5/3 is really equal to 1.6667. This rounds. We'll make an approximation because really this is a non-terminating decimal. But other fractions like, let's say 3/2, this is really 3 divided by 2, and that's the same as 1.5. So we can move to decimal values from fractions, but a lot of times we want to stay with fractions because they allow us to get exact answers, meaning we don't need to approximate. We keep precision, which is important. It's one of the powers of math. So all that to say what a fraction is, where it came from, and why we care. And now we're going to jump in and start playing with these things. So it turns out that the easiest operation to do with fractions is multiplication, and we need it to do some of the other ones. So we're going to start with multiplication. So 1/2 times 3/4. Another way to write this is, again, with parentheses. You notice the numbers being right adjacent to parentheses means multiplication. This dot here can sometimes be exchanged with the English word of, 1/2 of 3/4, right? That seems to appeal a bit to our intuition. I need 1/2 of the money in my wallet, right? Of means the product of 1/2 and whatever the thing is. So here we need 1/2 of 3/4. So I'm going to draw the pizza diagram one more time, and then you'll see how all fractions multiply because they use the same idea. So we don't need to draw it, but it can help kind of our intuition of why do we multiply the way that we do. So 1/2 of 3/4. Let's say we have a pizza party. Because we're so fun. Us math people, we're so fun. We throw pizza parties all the time. So this has been sliced into fourths. That's the type or the denomination, right? That's this guy. And I have 3 of them. So that's 1, 2, 3. And now we have a problem, right? We got a leftover pizza. We need to divvy it up evenly because I want half and you want the other half. How do you do that? Well, you might already be drawing in your mind with a knife where you would cut it to cut it evenly. and you might be trying to cut it right here, right? Which I'd actually agree with. You're right there, because if you think about the shaded area, it looks like that's been sliced in half. But in general, we need a process to do this, right? Because what if I said I wanted 1/3 of 3/5 of a pizza, or I wanted 1/8 of 7/10 of a pizza? We need something that works all the time. We can't just go in and find the perfect line. So what happens is we actually say, all right, you cut this up into 4ths, but really what we need to do is slice this up into 1/8. Because if we do that, now we've got this equal number of parts. We've sliced it up into the correct denominations that we can break it apart, right? And we can select what we need. So what just happened was the denomination became from 4ths, and it went into what? How many slices do I have? 1/8, right? So that's the new type. Again, it doesn't tell me how much pizza there is, but it tells me now how we have to slice the pizza to make it fair. And so now we're looking at, okay, what's 1/2 of this? And we saw before, if we just shade in 1, 2, 3 of those, that would be 1/2 of this. Ari gets really excited about pizza. So 1/2 is 3/8. Okay. So if I were to slice the pizza up into 1/8, having 3 of them is half. Okay. So where did these numbers come from here to here? Let's map this out down here really quickly. 3/8. I'll show you, and you might even already see it. You multiply the top to the top and the bottom to the bottom. And what you're left with is the resulting fraction. And this always works. Okay, so this is how we multiply fractions, and it will always result in the correct amount. So again, we're generalizing from one example, which is typically dangerous, but you can trust me, I wouldn't lead you astray. I proved this stuff back in the day. So let's do a few examples here. What's 3/4? We already did 3/4. Let's do what is 7/8 times 11/6. So again, drawing the pizza diagram here would be a real pain, but you know that the logic is going to hold up. What we do is we change the denomination to now be out of 48ths. All right, and I'll use blue here. To be out of 48ths, because 1/8 and 1/6 don't really line up, right? We're trying to talk about different proportions of different ways that the pizza's been cut. So to normalize that, we just say, all right, we're going to slice it up into 48ths, and now the top represents how many we have. That's 7 times 11, which is 77/48. So now again, where this lies on a number line, how I typically visualize it is looking at, well, what makes one whole? 48, and I have 77. So that means I definitely have more than one whole. I almost have 2 wholes, right? But not quite. So it's more like maybe 1.5 is around here. So you could verify in your calculator that I'm roughly correct. It should be around 1.5, 1.6, 1.7, something in there. So, and for now we can leave this as is. This is actually a simplified fraction, albeit improper. Okay. So this is how we multiply fractions. We're going to use this as a tool to convert fractions to needed forms, because we see that we can do that, right? We can change the way we slice things. We can change the denomination, and we're going to use it to simplify them, and then also to use them with division and addition and subtraction. Before we do that, I want to make a note here, which is that all whole numbers, or all, I should even say all integers, can be written as fractions. And the way that I mean that is if I take a look at, let's say, -2, the number -2, this is the same as the fraction -2 over 1. And this is a really, really important idea. It might seem silly, right? Why do we need two ways to write the same number? It matters big time. It matters big time. We need to be able to re-represent numbers and expressions over and over and over. So any integer can be written as a fraction by writing it over 1. Think about it. What is, and you can do it in your calculator, and you probably should just so that you believe me. Any number divided by 1 is itself. So if I took 100 and I divide it by 1, I'll get 100. If I took 10 billion and divided by 1, I'd get 10 billion. Yes, just to prove the point. It's worth doing. Prove to yourself that dividing by 1 is the same number. And so we will use this to our advantage, re-representing fractions, simplifying them, and combining them together. Because oftentimes we'll want to be multiplying a fraction times a whole number or an integer, and we'll need to do this conversion. So we're going to use that in this exploration. So I want to ask, how do we divide fractions? We know how to multiply them, but fractions already involve division. So how can we divide something that has division? Sounds kind of crazy. It's really not. So what we're going to do is highlight how we do it with a simple example. So 20 divided by 2. You can think you have a $20 bill and you want to divide it into 2. What are you going to end up with? We know we should end up with 10. Right? And why is that? We can take 20, slice it into 2 groups, and we get 10. What is equivalent to cutting something into 2 groups? Multiplying by a half. Right? So isn't it true that this is also equal to 20 times 1/2? It should be. And it needs to be. And if we use that fact that we said above about each integer being able to be written as a fraction, we'd see that 20 is really able to be written as 20 over 1. Mally, why are you doing that? I'll show you right now. How do we multiply fractions? 20 times 1 over 1 times 2 equals 10. And when we simplify, right, we remember those implied brackets on the fraction. We see that this is equal to 20 divided by 2, which we know is 10. Okay, so we know that these things are all equivalent statements. 20 divided by 2 is 10. It's the same as 20 over 2, but really the key idea is that this is equal to this. So this brings us to an important idea, which is that division is really just multiplication of the flip of the second number. Okay, and I say flip to kind of help us remember, but the word really is the reciprocal. So division is just multiplication of the reciprocal of the second number. So when you see 20 divided by 2, really it's equivalent to write 20 times 1 over 2. Right? What is the flip of 2? Well, if 2 is 2 over 1, then the flip, or reciprocal, is 1/2. So this is a key idea as well, the notion of reciprocal. So let's do an example here with fractions. Say I have 1/2 divided by 3/4. We'll flip the operation from before. We'll say evaluate this. So division is just the multiplication of the flip or the reciprocal of the second number. That's what this told us. Give me the reciprocal of the second number and make it multiplication instead. This always holds up. So this is the same as 1/2 times 4/3, because that's the reciprocal of 3/4. And now we're talking about multiplication, and we know how to multiply. This is 1 times 4 over 2 times 3, which is 4 over 6. And we'll talk about how we can simplify and reduce, but for right now, just to highlight that idea of division. It's always multiplying by the reciprocal of the second number. And another way you might see this, and it might seem intimidating, but remember it's just notation, 1/2 over 3/4, right? Isn't division the same as the fraction sign? It is. So this is really the same as 1/2 times 4/3. It's the same problem. It just looks different. And so this is also 4/6. Okay. So this is how we divide fractions. So you'll have a lot of practice, and I can't stress enough how much practice you should do with these, because if it's been a long time for you, then it will be that much more valuable, because this is gonna keep perpetuating throughout the course and through courses beyond. So this is really, really important to get a lot of practice. We can only do a few problems here, and the more practice you do, the more subtleties you'll understand. So we've got multiplication, we've got division, we see the different forms they come in, we roughly understand why they work the way they work, and now we're going to move into simplifying and reducing fractions, and then we'll get into addition and subtraction. And it's not that we're doing them last because they're harder, but it's because we need the other pieces first. So how do we reduce, simplify, or convert fractions? Sometimes we want to like unsimplify or go the other way on an equal sign. And so this will highlight how we do that. So we're going to start again with a half, because it's just the easiest one to kind of connect with. What I wrote here was a string of equality, saying 1/2 is equal to 2/4, and you might think about that and say, yeah, that sounds right. It's equal to 3 out of 6. Which is equal to 5 out of 10, which is equal to 10 out of 20. Right, so all of these things represent the same quantity. All these things represent the same quantity, which is if I have a whole and I slice it into 2, I've just got half of it. And that doesn't matter if I cut it into sixths or into tenths or whatever. It's going to be the same amount of the whole. And so the question is, how can we move between these things? Because obviously this goes on infinitely. I could do this until the end of time. Write equivalent fractions to just 1/2. And every other fraction has that same property, that you can infinitely write equivalent forms to representing the same number. Even the weird ones like 11/7, right? There's infinitely many fractions that are equivalent to that. That might be intimidating. It shouldn't be intimidating, but it should be astounding. Should be crazy. But we want to be able to move between each one, whether we want to reduce a fraction down to its simplest form, which 1/2 is, or pump it up to something like 10/20, because maybe we're working with 20ths, or maybe we're working with 16ths of an inch or 1/8 of an inch. How do we get from one to another? And so I'm going to show you that right now. One key thing here is to note that 1/2 is in simplest form. And how we know that, what this means is that top and bottom, or numerator and denominator, have no common factors. Okay, so that's what it means to be in simplest form. So what does that mean? It means all these other ones must have common factors, and they do. If we take a look here at 3/6, if we factorize the top and bottom, meaning write it as a product of their factors, we'd see, well, 3 is prime, so it's just 1 times 3, but 6 can be written as 1 times 6 or 2 times 3. And so this is what we call the prime factorization, because we're breaking it down to prime numbers. If you don't remember what prime means or composite means, prime just means it has no other factors other than itself and 1. Go ahead and Google prime and composite numbers if you'd like a breakdown of that. But really just breaking it down into its simplest Lego blocks. So 6 is 2 times 3, 3 is 1 times 3. And we see here what we're talking about with common factors. There's a 3 in the top being multiplied and a 3 in the bottom being multiplied. And so what we get to do is go the other way on our equal sign from multiplying before and say, well, I know that this must have come from then 1/2 times 3 over 3, right? Because don't we remember going this way where we multiply two fractions and then combine them over the same bar? Now we're going the opposite direction and saying 1/2 times 3 over 3. Well, what's 3 over 3? It's 1. And what's anything times 1? Itself. And so this is how we're left with just 1/2 in simplest form. Same thing happens with 10/20ths, right? Let's bring this down here. So 10 over 20. Well, you can write this as 1 times 2 times 5. And the bottom as, and we can include 1 down here. I didn't do it before, but 1 times 2 times 2 times 5. And what are we left with? 1 over 1 times 2 over 2 times 5 over 5 times 1 over 2. And I'll explain why there's that extra 1 up there. But what do we see? We see all of these cancel except for the remaining 1/2. And so this is equal to 1/2. So why were we left with a 1 in the top and not a 0? Well, there's a few answers for that. The first is that we can't be left with nothing. But when factors reduce, right, and they're canceled out, how do we do that? We do that by dividing the common factors, and the resulting remainder is 1. So that's one way you can think about it. So if you cancel common factors and there's nothing left in the top or in the bottom, this could happen as well, just know that it's not 0, it's 1, because you haven't been subtracting anything. There's no way to divide and get something to 0. All right. So this is the way that we reduce fractions. And you can see how just going the opposite way can get us to pump up fractions. So let's look at it like this. Convert 3/7 into, let's say, 21sts. So what we have to do is say, well, I have 3/7 and I want this to be, out of 21. What's the equivalent fraction to get it out of 21? So I've got something sliced into sevenths, but that wasn't enough, and I need things sliced up into 21sts. How do I do that? Well, we need to see what I need to do to the denomination to get it from here to here. So you might see, okay, well, to get 7 to 21, I need to multiply it by 3. That would get me to 21sts, right? So that'd be good. But I can't just go around multiplying numbers by any old number, right? So I can't just take a 7 and multiply it by a 3. If I did that, or you could do that, I would just multiply all the money in my wallet by 3 all day long and retire at the age of 34, right? So we can't do that. But what we can do is multiply things by 1. You're allowed to do that without reporting it to the IRS. You can multiply the money in your wallet by 1 because what do you get? You get back the same number. So how do I multiply a fraction by 1? You multiply a fraction by 1 by multiplying by the same number over itself. So in this case, 3 over 3. So multiplying by 3 over 3 is okay, because again, this is common factors. And what happens? We result in getting 3 times 3 over 7 times 3. The top becomes 3 times 3, which is 9. So this gives us 9/21 is the equivalent of 3/7. And so you'll have some practice with this of converting fractions into different types. And we'll do it as well right now as we move into adding and subtracting fractions. Okay, so you know how to multiply and divide fractions. You know how to convert and reduce fractions. And again, for each of these, jump in and do just as many examples as you can. Make flashcards, go crazy, because the more that you do now, the better you'll do later. You'll thank yourself later. Just please trust me on this one thing. So adding and subtracting fractions is last, and then we'll maybe do exponents at the end to see just the whole order of operations, how it should work. But adding and subtracting. How did I describe this last time? I said that this is the slowest operation, because it's really the idea of totaling or putting into buckets. You might be saying to yourself, Mally, why are you talking about buckets? This is math class. The reason is because totaling is really just like putting into the cash drawer. If you've ever had a cashier job before, you have to put the correct denominations in each slot, right? So you don't put the 20s in the 1 slot, you don't put the 1s in the 50 slot. When you're totaling them, putting them into their buckets or into their correct rows, you need the denominations to be correct. And the same thing happens for when we're totaling up fractions. These are parts of a whole. And so if we don't have them lined up to be with the correct type, then we can't possibly add them together, right? What's a half a pizza plus 3/4 of a pizza? I don't really know how much that is. What's 3/8 of an inch plus 5/16 of an inch? I don't quite know. And so that's what we're going to do right now, is to put them into the cash drawer, need to be converted first. Need to be type converted first. Okay? So with this slowest operation, we actually have to be the most careful, because they have to be the same type. And this is an idea that we'll continue into when we get to algebraic expressions with variables. Things need to be of the same type. And adding and subtracting is slow. Putting them into the buckets is slow. So how do we do this? Let's look at a measurement example, right? What is 3/8 of an inch plus, let's say, 5/16? I'm measuring out a door frame. I need these pieces of trim to line up. 3/8 of an inch plus 5/16 of an inch. How long is that total for that gap or that length? Well, on a ruler it's pretty clear because everything's sliced up, so you can kind of mix and match between the types. But on paper, or in a computer, we need to do this slightly differently. We don't have that kind of graphical display of the tape measurer. But 3/8 plus 5/16, what you essentially do is say, well, I need to not be in eighths anymore. I need to bump up to 16ths, because that's the most specific slice. That's the most specific type of number or denomination of the measurement. So if we go 3/8 plus 5/16, we identify that the common type, which is also called the least common denominator, if you remember or have heard that term, is 16ths. So what this tells you, once you find this part out, what the common type is going to be. Now you need to convert everything to that common type. Convert all fractions to this type. Okay, so how do we do that? Well, this guy is already good to go as 5/16. Sometimes it isn't the case. 3/8 is not there yet. So we got to think about how do we get 3/8 to 16ths. So 3/8 times what over what gets me something out of 16. Well, 8 times 2 is 16, so it must be 2 over 2. And so how many 16ths is 3/8? It's 3 times 2, which is 6. Okay, so now this guy is, and I often do this, I'll put the side work off to the side to kind of inform the main stream of thoughts here. So this really becomes 6/16. And so 6/16 and 5/16, how much is this total? Well, again, remember that the 16ths are telling you what? The type. It tells you the denomination. How many, if we had a $16 bill, right? I have 6 $16 bills and 5 $16 bills. How many do I have total of the $16 bills? You have 6 plus 5 all over 16, which is 11/16. Let me say here, people are very tempted to add the 16s together, and I see why. They're just sitting right there. But if you remember what that represents, that won't be a problem for you. So just remember that this is the type, right? It's the dollar bill. So if we're talking about how many 20s do I have, if I had 6 20s and 5 20s, I don't somehow have 11 40s, right? That now I just doubled the amount of money that there is, so we can't do that. So again, I stress this point just because I've been teaching this course for a really long time, and I see this as a place where students get into trouble. And so if you can mitigate that now through practice and asking good questions, you'll be so much better set up for success. So we converted all fractions to the type of 16ths. What did we do next? Now we combine with addition over that same type. So it was here. And then simplify. What does simplify mean? It means just reduce symbols. Reduce the number of symbols and numbers. Not using your eraser or anything, but using the rules of math to reduce it, get it as concise as possible. So this is as concise as possible. So let's try one more here, because this is a big idea. Let's do 3/4 minus 5/6 plus 11/10. Now what I want to do, I want to look at this first and get a sense of where I should end up. That's a good mathematical mindset. Do I have some idea of where I'll end up? Not to be in a fixed place with it of I know exactly where I should be, but a rough idea to see, does my expectation line up with my solution? Because if it doesn't, then that might be a place for a question mark, right? So I look at this and I say, okay, 3/4, that's less than 1. It's about 3/4, it's about 75% or 0.75 minus 5/6. All right, so that's a little bit closer to 1. So I might be like negative there. I might, like when I subtract it, I might be slightly less than 0. But then I add 11/10. 11/10 is bigger than 1. So that's probably going to shoot me back across into the positive. So I'm thinking I'm probably going to end up slightly positive with a resulting fraction. Okay. So first kind of get a sense of end result. It's not always possible, but give your brain a frame. If you have a frame, you kind of cut down on how much you need to manage. So get a sense of the end result, and even if that sense is, I'm not really sure where this is going to end, that's okay. 2 is identify the common type, common denominator, or common type between all 3 fractions. That's going to be the easiest thing to do. The surefire way to get a common type is to just multiply the denominators together. Okay, so this will not result in the least common denominator, which is ideal because you're going to be left with the simplest form. But sometimes just factoring them all together just makes it a lot tougher. So if we just multiply the denominators together, we will get a common multiple, right? Because if you multiply 6 and 4, you get 24. You know, both of those end up there. So that is a slice that would work. But if we multiply them all together, then you will be left with the type that will work for everything. Okay. It will inflate the numbers, but we just kind of deal with that. So this is what I recommend doing in general. And as you get more comfortable with it, you'll start to see what maybe a lesser common denominator would do for you, and you might be able to spot them more easily. So to get any common type, multiply the denominators. So what is that type? Well, that is 4 times 6 times 10, which is 240. Just a number. It's bigger than we've seen probably in a while, but no sweat. 240. So the question is, okay, how do I get these things to being equivalent to 240ths versions of themselves? Converting the dollar bills, right? Converting the denominations. So how do I get 240, or how do I get 3 into 240ths? So for this first one, how do I get 3 to 240ths? Well, we have to convert it by using the same fraction we did to get 4 to 240ths, right? So this process times what over what gives me 240ths. So how do we figure out 4 times what gives me 240? Well, I'm guessing that you don't have memorized the factors of 240, as neither do I. But the way that you can do this is just say 240 divided by 4 must give you that number. And you can use your calculator to find that that should be 60. So this is like the multiplier that we need for this fraction to get there. So then we can't just multiply things by 60, so we multiply it by that fancy version of 1, 60 over 60. And then in the top, 3 times 60 gives us 180. So 180 out of 240 is the same as 3/4. Okay, and so we do this for each of these. Might hear my boy crying in the background. He loves fractions just as much as the rest of us. So 5/6 times what gives us something out of 2/40ths. So again, same process, 240, but divided by 6 now gives me 40. So that's the multiplier I need here, 40/40ths. And so 5 times 40 is 200. So that's this one. And then lastly, the tenths, 11/10. 11/10 times what gives me 240ths. So to convert the tenths to 240ths, we must have needed 24. So by 24ths, and 11 times 24 is going to be what? 263? Let me double check that. 264? Yes, so it's 264. And so that goes up here. So now we've got everything converted to the correct type. And so now we can put them all into that drawer, right? This is all going into that cache drawer of the 240th. How many do we have now? Well, now it's 180 minus 200 plus 264 for a grand total of, well, 180 minus 200, we do them order of left to right, 180 minus 200 is negative 20, plus 264 gives me 244. And it's okay to use your calculator here. We very much want to be using that tool. So looking at this, you might not see that this is not a simplified fraction. I do see that. And so what I usually start off with by noticing is the top and bottom, are they both even numbers? If they're both even numbers, you know that you can simplify it by at least a factor of 2, right? Because any even number is a multiple of 2. So what I might do is rewrite this as 2 times something over 2 times something and figure out what those somethings might be. So this would be 244 divided by 2, which is 122, and 240 divided by 2 is 120. And so we can cancel out those 2's. We can actually do that again, right, with the resulting fraction to try to get it to the simplest form. So again, 122 divided by 2 is what, 61. Right, yes, goodness. And then 120 over 2 is 60. So this is equal to 2 times 61 over 2 times 60, and that is 61 over 60. And you notice we can cancel these common factors. And we're left with 61 over 60, which is in simplest form. And why is that? It's because 61 is prime. There's no other factors besides 61 and itself, so it can't possibly have any other factors with 60. So this is as good as it gets. This is what we call simplest form. So from beginning to end, that was kind of a lot of work, but over time this will speed up, right? Obviously when I'm doing these problems myself, I don't break them down step by step because I'm comfortable with all of these steps. But for you to start off, you should absolutely be doing each of these steps. So what did we do just to finish off our to-do list here? Get a sense of end result, identify the common type, multiply the common types to get it, or multiply the denominators to get that common type, and then convert them, right? So kind of our third step was convert each. This was more intense than the last one because in the last one, our common type was already held by one of the fractions, right? The 16th was the common type. But if you don't have that, or it's not easily observable, then to just make up the common type by multiplying the 3 or 4 that you have, whatever it is, and then convert each. And then we combine. I wanted to leave my to-do list on one side, but we'll just map it over to here. And then simplify. So roughly like a 5-step process. Will they all be exactly like this? No. If you're looking for these math problems, these computation problems to all be the same, in some ways they will be. There are rules that can't be broken, but in other ways they're all so different by just little shifts that it won't always follow exactly the same. But in general, they will have this sort of structure of get a sense of it, identify common type, convert them all, combine them all, and simplify if you can. So, we've done a lot. What have we covered so far? Let me scroll back to the top. We talked about where fractions came from, right? We didn't used to be able to represent numbers this way. And again, if you feel like this is complicated, look at the hieroglyphics for fractions and tell me if you prefer these or not. I mean, sure, hieroglyphics are more fun, but this is a lot simpler, a lot nicer to work with. What is a fraction? It's a parts to whole representation, right? It's a comparative quantity, top to bottom. The bottom holds the type, and the top holds how much. That's why when we total them up, you don't add the bottoms together, but when we multiply or divide, we change the slicing. And how do they work with each of these operations? So we looked at these. We didn't look at exponents, but since this is just repeated multiplication, this is not beyond you at all. I think you've got that in the bag. And so we know how to work with the order of operations with these things. We saw how to represent them. And there is one last point that I wanted to talk about. Zero and fractions. And this is a really big idea. So with zero and fractions, how do they play together? If I have 0 over 4, what does this mean? Well, my type is 4, right? So if we're talking about a whole, I've sliced it into 4 pieces. How many do I have? None. Okay, so I have none. So this equals 0, right? Because you look at how we've sliced up a whole and I have none shaded, so this is really equal to 0. And this works for any number. 0 over any number will always be 0 because of this fact. Slice it up however you like, as long as I don't take any slices, so that's going to be 0. Simple enough idea, right? Now, here's where people get into trouble. If I had 4 divided by 0, what does that mean? Well, how do I slice up my types? 0 slices, right? That's very, very confusing. Now, you might be thinking, well, just put out the whole, Mally, right? That's 0 slices. Not really. This is 1 slice because it's all one piece, right? So this would be with a denominator of 1. A denominator of 0 makes no sense, right? We can't slice in zeros. We can slice in 1 wholes, right? Have the whole thing. But you can't slice in zeros. You can't divide into zeros. Another way to think about this, right, is if I take 0 and divide it into 4 groups, how many do I have in each group? 0. This one says if I take 4 and divide it into 0 groups, again, that doesn't make sense, right? It's not take all of the 4. That would be 1 group. Take 4, divide it into 0 groups. It doesn't make sense. And so for that reason, when we try to divide by 0, we say this is undefined. Oop. Pen glitch there. Sometimes in the software, you might write in the answer DNE, which stands for does not exist. And so notationally, people can look at this and say, it's a small change, 0 divided by 4 versus 4 divided by 0. It's really not a small change, and it's because division, the order matters greatly, right? 4 divided by 2 is not the same as 2 divided by 4. In the same way, these things are not equivalent, and one of them is catastrophic, right? This actually blows up our number system. You cannot divide by 0. It's one of our biggest rules. And to kind of foreshadow a little bit, when you get to calculus, that's when we created this genius idea to get around this issue, but for a very specific use. However, in just straight computation, you can't divide by 0. So go ahead and try this in your calculator. Try for both and see the difference. And you might be saying to yourself, this is a waste of time, I'll just trust them. You need to show yourself that this is the case, because this will come up a lot. Not even in just straight computation problems, but when we get into more manipulation of algebraic structures, knowing when the denominator is 0 versus when the top is 0 is a huge idea. Huge idea. So please make sure that you've got this straight and you see that this bottom one here is something to be noted with a red flag, and that this top one is, it's okay, it's just 0, right? And 0 isn't undefined, it's a defined quantity. So it means nothing. So that is the end of this lecture here. Again, we did some easy to medium level problems for computation. I encourage you greatly to do every problem that's in the textbook, every practice problem, and then probably more. If you're not feeling very, very comfortable with this by the end of that, I will link some other resources for you to check out, because the more you can practice, the better. There are some places that have courses just on fractions and decimals for a whole semester, and we're doing this as like 1 unit. So just to highlight the importance here of practice. So have fun, hit the class discussion. I look forward to talking with you guys about this.